বলেন। ইয়েস, ইকো হচ্ছে। হুম, 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 হুম। আজকে আপনি আপনার ইউটিউব থেকে করবেন না, ঠিক আছে? আজকে আমি আপনাকে লিংক বলে দিচ্ছি। আপনি যেটাতে গড়বেতা, যেটাতে আপনার কলেজে ঢুকেছেন, মানে যেটাতে ওবিএস করছেন, ঠিক আছে? সেখানে আপনি আহ, না, একটা অল্টারনেটিভ লিঙ্ক আমার তো দুটো অল্টারনেটিভ লিঙ্ক বানানো আছে। সেটা কালকে বানানো ছিল, ঠিক আছে? আজকেও সেটা আমি কনভার্ট করে নিয়েছি আজকেরটাতে, কালকে যেহেতু লাগেনি। এবার তাহলে আজকে তো ম্যাক্সিমাম একবার যদি যদি কখনো কাটে, কারণ আবার note করেছে। তো আপনি অল্টারনেটিভ লিঙ্কটা থেকে, যেটা আমি ওটা আসলে ড্রাফট করে রেখেছি মেলে, বুঝেছেন? ওটা আসলে ড্রাফট করে রেখে আপনি ওই যেটাতে ওবিএস এ বসিয়েছেন, সেটাতে আপনি এই ওয়েবিনার গড়বেতা কলেজ থেকে যান স্টুডিও, ইউটিউব স্টুডিওতে। সেখানে দেখবেন ওটাতে 2A দিয়ে একটা ভিডিও শিডিউল করা আছে। আমার মনে হয় না অবশ্য লাগবে, এটা ঠিকই। হ্যাঁ। ও, হ্যাঁ। ও, আচ্ছা শুনুন না, আপনার জিমেল আইডিটা আমাকে দিয়ে রাখবেন তো। হ্যাঁ, আপনি আমাকে হোয়াটসঅ্যাপ করে রাখুন না জিমেল আইডিতে। আচ্ছা, 12 তারিখ বিওএস হবে। হুম, সন্ধ্যে 8টায়। হ্যাঁ, 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 হ্যাঁ। সেটা কি, সেসব কিচ্ছুই জানি না। মানে আমি আপনাকে বলে দিচ্ছি একবার, এটা দেখিয়ে দেবো এজেন্ডা গুলো। দাঁড়ান, আমি প্রেজেন্ট, ও না, এখানে তো present করতে পারবো না। ঠিক আছে, আমি হোয়াটসঅ্যাপে পাঠিয়ে দেবো। আসলে না, ওনারা না চেয়েছেন, চিঠি চেয়েছেন। ফলে আমি এই আপনার এই প্রোগ্রাম চলতে চলতেই চিঠি দুটো লিখে প্রিন্সিপালকে দিয়ে ওদেরকে মেল করতে হবে। আবার আমি মেল করলে চলবে না, কেন বলুন তো? যেহেতু মানে বোর্ড অফ স্টাডিজের চেয়ারম্যান। আপনি বাচ্চাগুলোকে দেখান। আমি বলছি আপনার বাচ্চাগুলোকে দেখান। আমার ছেলেকে ইউটিউব ছায়াময় দেখাতে বসিয়ে দিয়েছি। হ্যাঁ, 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 ঠিক আছে, ঠিক আছে। স্যার, আমার এখনো কিছু লেখা হয়নি। আমি স্যার এই প্রোগ্রাম শুরু করে দিয়েছে, চিঠিগুলো লিখতে বসবো। স্যার শুনতে পাচ্ছেন?
হ্যাঁ, হ্যালো।
হ্যাঁ স্যার, বলছি আমার এখনো চিঠিগুলো লেখা হয়নি এই
হ্যাঁ, ঠিক আছে।
প্রোগ্রামে বসে।
যেটা শেষ হোক না, শেষ হলে করে পাঠাবো।
কারণ আজকের মধ্যে পাঠাতে হবে, তো যেটা বুঝলাম আর কি, তার কারণ 12 তারিখ যদি হয় তাহলে তো আজকে পাঠাতে হবে।
আরে আজকে কাল সকালে পাঠালেও চলবে, এত তাড়ার কিছু নেই।
পাবে। ইউনিভার্সিটির রেগুলেশন কি কিছু দেখেছেন?
না, দেখি পিজি। না, পিজি রেগুলেশন তো দেখি কিছু। ওদের তো পিজির বেরোয়নি, একটাই বেরিয়েছে।
ঠিক আছে সব
অভিজিৎ দা, আপনি ওয়েবিনার গড়বেতা কলেজ থেকে মিউট করে দেবেন না, যে ওই অভিজিৎটাকে মিউট করবেন, কোনো একটাকে আর কি মিউট আর ভিডিও।
ওয়েবিনার গড়বেতাটাকে মিউট করব।
হ্যাঁ হ্যাঁ, ভিডিও আর ইয়ে অফ করে রাখুন। হ্যাঁ, এবার ঠিক আছে। হ্যাঁ হ্যাঁ হ্যাঁ, এক সেকেন্ড। হ্যাঁ, বলুন কোয়েশ্চেন। আচ্ছা, আচ্ছা, আচ্ছা আচ্ছা, ঠিক আছে, আমি বুঝতে পেরেছি, আমি করে দেবো। আমাকে হয়তো 1-2 ছেলের কাছে যেতে হতে পারে। হ্যাঁ, ওই আমি কি করি বলুন তো, ইউটিউব থেকে ওই কপি করে প্রথমে নোটপ্যাডে নিয়ে নিই, নোটপ্যাড থেকে গুগল মিটে কপি পেস্ট করে দিই। ও হ্যাঁ হ্যাঁ হ্যাঁ, সেটা করা যায়, কিন্তু অনেক সময় সব ইয়ের অ্যালাইনমেন্ট ফ্যালাইনমেন্ট চেঞ্জ হয়ে যায় বলে আমি সব ঠিক আছে, কোনো প্রবলেম নেই। আচ্ছা আচ্ছা, ঠিক আছে ঠিক আছে, ঠিক আছে। 2:56 বেজে গেছে, স্যারকে একটা ফোন করে, প্রিন্সিপাল স্যারকে একটা ফোন করে দিচ্ছি। বাবু এসেছেন? অভিজিৎ দা, স্ক্রিপ্টটা আর কিছু করার দরকার নেই, ঠিক আছে তো গোটাটা? স্যার চলে এসেছেন। আর কেমন আছো বিশ্বজিৎ? কেমন আছো বিশ্বজিৎ?
হ্যাঁ ভালো আছি, আপনারা ভালো আছেন তো?
হ্যাঁ 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 ভালো আছি। হ্যাঁ 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 ভালো আছি। আমাকে একবার আপনি হ্যাঁ হ্যাঁ ওটা মিস করে গেলে মুশকিল। দাঁড়ান ওটার সঙ্গে ছোটানো কিছু কাজ বাকি। হ্যাঁ, ঠিক আছে শুরু করার পর করবেন। এই ফিডব্যাক দিতে আজকে। হ্যাঁ 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 জয়েন করে গেছেন। সৌরভ বাবু জয়েন করে গেছেন। হ্যাঁ 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 স্যারের সঙ্গে একটু পরিচয় করিয়ে দিন অভিজিৎ দা।
গুড আফটারনুন। ওয়েলকাম 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 সৌরভ বাবু। সৌরভ দাস। সৌরভ দাস।
স্যার আপনার কথাটা আজকে একটু আস্তে আসছে।
কেন শোনা যাচ্ছে না?
আপনার কথাটা একটু একটু আস্তে আসছে দূর থেকে।
ঠিক আছে, আমি তো কালকে এভাবেই বলেছি, আমি নেটওয়ার্কটা দেখে নিচ্ছি। হ্যাঁ
এখন ঠিক আছে।
না, আমি নেটওয়ার্কটা চেক করছি, নেটওয়ার্কের সমস্যা হতে হবে। ঠিক আছে।
হ্যাঁ স্যার,
ঠিক আছে ঠিক আছে এরপরে
আচ্ছা ঠিক আছে।
মনে যাচ্ছে তো?
আচ্ছা স্যার আপনি একটু ইয়ারফোন ইউজ করতে পারবেন কি?
হ্যাঁ
আপনি স্যার ইয়ারফোন ইউজ করতে পারবেন কি?
চেষ্টা করছি আমার একটু অস্বস্তি হয়, এগুলো করি না। ঠিক আছে আমি করছি।
মোল্লাদা জয়েন করেছেন। হ্যাঁ তাহলে আমি এয়ার করছি, মানে ব্রডকাস্ট করছি। ঠিক আছে। হ্যাঁ 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 হ্যাঁ
লেট আস স্টার্ট।
একটা খালি একটু আমি ক্লিয়ার করে নিই, সৌরভ বাবুর একটাতে দুটো মেশিন থেকে উনি জয়েন করেছেন। একটাতে যেটাতে ভিডিও আছে সেটাতে অডিও নেই, আর যেটাতে অডিও আছে সেটাতে ভিডিও নেই। স্যার এটা কি আমি ঠিক বলছি?
আমাকে বলছেন?
হ্যাঁ হ্যাঁ আপনাকে বলছি।
হ্যাঁ হ্যাঁ, আমার অডিও মেশিনটা আলাদা আছে আর ভিডিওটা আলাদা আছে। আমি ভিডিও অফ করে দেবো একটু পরে
ওকে না
প্রেজেন্টেশন।
স্যার। আচ্ছা আচ্ছা ঠিক আছে ঠিক আছে স্যার, তাহলে শুরু করছি আমি।
অ্যাকচুয়ালি মোবাইলে সাউন্ড কোয়ালিটিটা ভালো যায়।
Good afternoon, everybody. Our today's session is about to begin now. I would like to invite Professor Dr. Hariprasad Sarkar, Principal of Gorbeta College and the chief patron of this program, to deliver today's welcome speech. Sir, please.
Okay. Am I audible? Am I audible clear?
Yes, sir.
Yes, sir. Yes.
Good afternoon, everybody. Welcome to all on the second day of our webinar entitled Enrichment Program for Students and Teachers, first page, on linear algebra analysis and differential equations, organized by the Department of Mathematics, Gorbeta College. And I heartily welcome today's speaker, Dr. Saurabh Das, Assistant Professor, Department of Mathematics, National Institute of Technology, Jamshedpur, and also Dr. Bikash, who will also speak today, Assistant Professor, Department of Mathematics, Constituency, Vivekananda Centenary College, Rohada. And thank you all, the organizers for arranging that type of seminar, today's seminar, the engagement program for the students and teachers. Yesterday, we have an eminent speaker, Professor Sujit Kumar Sardar, Professor Department of Mathematics, Jadavpur University. And yesterday's program also was very much successful with a long discussion by this eminent speaker, Dr. Sujit Kumar Sardar, nearly about more than 3 hours. And I thank to him for his lecture. And like yesterday, I think today's program will be highly successful. And after all the participants will be highly benefited from their lecture by the Dr. Saurabh Das and Dr. Bikash Chakraborty. And it is about my introduction and welcome address to the speaker and all the participants in the today's webinar. Thank you all.
Sir, thank you for your... Am I audible? Sir, thank you for your speech. And I convey my heartfelt gratitude to you for being with us throughout this program and continuously inspiring us. As mentioned by our principal, sir, today we have the privilege to have two eminent mathematicians, Dr. Saurabh Das and Dr. Bikash Chakraborty, among us as the distinguished speakers. Now I would like to introduce Dr. Saurabh Das, the first speaker of today's session. Research interests of Dr. Saurabh Das includes complex analysis, orthogonal polynomials, and special functions. He has received his BSc in Mathematics degree from University of Kalyani, and he has received MSc and PhD degree in Mathematics from IIT Roorkee. After that, he joined National Institute of Technology, Hamirpur, as a lecturer in the year 2017. Then he joined National Institute of Technology, Jamshedpur, as an assistant professor in the year 2018. He has published several research articles in various reputed international and national journals and delivered talks in international conferences in India as well as outside India, like London, Austria, Malaysia. He has also delivered several expert lectures in various workshops, short-term faculty development courses, and webinars. He has received Best Publication of the Year 2017 by the Society for Special Functions and Their Applications. He is also editor of Far East Journal of Mathematical Sciences. He is reviewer of various international journals like Ramanujan Journal, Indian Journal of Pure and Applied Mathematics, Advances in Difference Equations, and Mathematical Reviews. He is also a member of American Mathematical Society, Society for Special Functions and Their Applications, and Foundations of Computational Mathematics. The title of his today's talk is Orthogonal Polynomials and Applications. Now I would like to invite Dr. Saurabh Das to deliver his speech. Sir, please.
Okay. Thank you, Professor Rajashri. First of all, I would like to thank the organizers, the chief patron, Dr. Hariprasad Sarkar, principal of Gorbeta College, and the coordinator, Pritish Kumar, and special thanks to the conveners Dr. Abhijit Banerjee and Dr. Rajlakshmi Mukherjee for their day and night efforts for this event. And I would also like to thank the head of the department, mathematics, for this event. So today I'm going to discuss about orthogonal polynomials and applications. I'll just share the slides. Just a second. Okay. Are the slides visible?
Yeah, it's quite clear.
Am I audible?
Yes, yes, sir.
So today we are going to discuss about orthogonal polynomials and applications. The pioneer of orthogonality. This is the photo of Chebyshev. And if you open any book of orthogonal polynomials or basic undergraduate book, first polynomial we can see is the Chebyshev polynomial. It's the common, and we can see different kind of spelling like that, Chebyshev, Chebyshev, like that, but all are correct. Actually, orthogonality of functions were initially defined by Murphy in 1835. Later, Chebyshev realized their importance, and his work since 1855 was motivated by the analogy with Fourier series and by the theory of continued fractions and approximation theory. We will discuss all these things in a later stage, and how orthogonal polynomials are important and how orthogonal polynomial play vital role in approximation theory and theory of continued fractions and our real life problems. So first of all, let us discuss about why should one study orthogonal polynomial? Why should we know about orthogonal polynomials? So answer is not simple, means there are so many answers available, but first answer I would like, since so many undergraduates, graduates and others students are there and other members are there, so I started this answer with a simple theorem. What is just approximation theorem? This is very famous theorem. This theorem says that any continuous function on a closed and bounded interval can be uniformly approximated on that interval by a polynomial to any degree of accuracy. Let us simplify the thing. For example, suppose fx is any continuous function in a closed interval ab, and obviously f is real valued, and then there exists a polynomial px such that mod of fx minus px is less than epsilon. That means if we have a continuous function, we can all in a closed interval ab, then we can always approximate it by a polynomial. Now someone can ask me a question, okay, px is any polynomial, then why should you discuss about orthogonal polynomial? since we are talking about approximation here, so definitely error comes into the picture. Whenever you are approximating a function by polynomial, some error will come. So instead of any arbitrary polynomial, if we use orthogonal polynomial, we will get less error. Now, we move towards the importance. Orthogonal polynomials are important as has so many applications in approximation theory, theory of numerical quadrature, minimizing the error caused by interpolation, and mathematical physics, and different branches of science and engineering. But one thing we should keep in our mind that when we use orthogonal polynomial for approximation, so rather than just power of x, it is necessary to use higher degree polynomial. So to get the better approximation and to get less error. So let us first define orthogonal polynomial. So suppose that we have a polynomial, sequence of polynomials, p and x, and it satisfies this orthogonality property a to b wx pnx pmx dx is equal to kn delta nm, where kn is positive. Here delta nm is the Kronecker delta, and here the notation pn pm is the inner product. So if this inner product satisfies this property, we call this is this sequence of polynomial pnx is orthogonal with respect to the weight function wx. If you are familiar with measure, then we can exclude this weight function, and instead of writing dx, someone can write pnx pmx d mu x is equal to kn delta nm, where mu is positive measure, and if mu is absolutely continuous, then d mu x can be expressed as wx dx. So both are equivalent definition, but for our simplicity, we are just taking wx as weight function. So before going for different kind of polynomials, let us characterize orthogonal polynomials. So an orthogonal polynomial can be characterized in two parts or two ways: classical and non-classical. Classical polynomials also can be separated in two parts, or it can be discussed in two ways. One is infinite, another is finite. Now someone can think that why infinite comes into the picture, because whenever you are talking about polynomials, that means it has a fixed degree n. So for example, x to the power n plus something plus a1 x to the power n minus 1 and so on. But you don't think in that way. Here infinite and finite, what is the difference between infinite and finite, we'll discuss later. It depends on the orthogonality relation. We'll discuss it later. And classical orthogonal polynomial, okay, we discussed about infinite and finite, and infinite polynomials has three different kind of three members: Jacobi, Laguerre, and Hermite. Some people used to call Hermite. And finite class of orthogonal polynomials, classical orthogonal polynomials, has members called Romanowski or Romanowski polynomials. Romanowski polynomials again has three parts: first class, second class, and third class. And it is also known as R Jacobi, R Laguerre, R Hermite. R stands for Romanowski. Similar way, non-classical orthogonal polynomials has two parts: quantum and discrete polynomial. So in this talk today, we'll discuss mostly about classical orthogonal polynomials or hypergeometric orthogonal polynomials. Again, Jacobi polynomials has some particular cases, and mostly when we see some books, we find this kind of polynomials: Legendre polynomial, Chebyshev polynomials, ultraspherical polynomials, Gegenbauer polynomials. So most of the books in undergraduate books I saw, it's like Chebyshev polynomials, these are common. So how can you get this kind of polynomials? So Jacobi polynomials are denoted by P and alpha beta x. So if you put alpha is equal to beta is equal to 0, Jacobi polynomial will imply or reduces to Legendre polynomial. If you put alpha is equal to beta, then it will become ultraspherical polynomial. If you put alpha is equal to beta is equal to lambda minus half, then it will give you Gegenbauer polynomial. And similarly for alpha is equal to beta is equal to minus half, we get Chebyshev polynomial of first kind. And generally Chebyshev polynomial of first kinds are known as Chebyshev polynomials. And alpha is equal to beta is equal to plus half, we get Chebyshev polynomial of second kind. So these are some family of classical orthogonal polynomials. So another name of classical orthogonal polynomial is hypergeometric orthogonal polynomial. Why people call it as hypergeometric orthogonal polynomial? Because any classical orthogonal polynomial can be expressed in terms of hypergeometric functions. So what is hypergeometric function? Let us see first, because to discuss about orthogonal polynomials or classical orthogonal polynomials, we need the help of hypergeometric functions. So hypergeometric function, before going for general hypergeometric function, let us first discuss about Gaussian hypergeometric function. So it's obvious that it was provided by Gauss. This is a photo of Gauss. So let us consider Gaussian hypergeometric differential equation. And we can see that it's a second order linear differential equation, and it has three regular singular points, 0, 1 and infinity. And since it is second order differential equation, we have two independent solutions, linearly independent solution. So how to solve this hypergeometric equation? So this is a differential equation with variable coefficients, and on simple method is to apply Frobenius method, or you can say series solution. So here you can see that x is equal to 0 is an ordinary point, and if you solve it using Frobenius method, we can find the series solution like that, provided c not equal to 0 and negative integers. So for c non-zero and non-negative integers, a solution of this Gaussian hypergeometric differential equation can be obtained like that. Here we have used on symbol alpha n. This is known as Pocamer symbol. Here alpha naught is equal to 1 and alpha n is equal to alpha plus 1, alpha 2 plus 2 and alpha plus n minus 1. And if you see it in a deeper way, if you zoom it, you can see that it is nothing but your related to factorial n. Put alpha is equal to 1 here in the last in this, then you can see that it is giving us factorial n. So Pocamer symbol generalizes the concept of factorial, and alpha n can be expressed also in terms of the ratio of gamma function. Here we can see that alpha n is equal to ratio of gamma alpha plus n and gamma alpha. One thing we should keep in our mind that alpha should not be negative integer and 0. Why? Because gamma function is not defined for 0 and negative integers. So why the name hypergeometric? Because here you can see the red mark, the coefficient red here, AK, BK, bifactorial K, CK. Actually, it generalizes the geometric series. If we put alpha is equal to 1 and beta is equal to b, gamma is equal to b, so you can see here like this, 1k, bk factorial k. So 1k, Pocamer of 1k is nothing but factorial k. So ultimately we'll get geometric series. So geometric series is a particular case of hypergeometric series. That's why that series is known as hypergeometric, because it generalizes geometric series. And this hypergeometric series has 2f1 has integral representation of this form. Now, next question is that, can we generalize this hypergeometric series? So it's true, and a generalized form of hypergeometric function can be expressed like that. So initially what we did in terms of in the form of Gaussian hypergeometric series. So Gaussian hypergeometric series, we had AK, BK in the numerator and CK in the denominator. So if we take M times A1, A2 and AM, and here in the numerator N times, then we can get a generalized version of Gaussian hypergeometric series. We call it generalized hypergeometric series. Now, another important question here is that after solving, we are getting this, after solving this Gaussian hypergeometric equation using Frobenius method, we are getting this one kind of solution. What is the guarantee that this series will converge? Because if it is divergence, then it is of no use. We need convergence. So similar way, so we will discuss the convergence of Gaussian hypergeometric series or function. So you can check the convergence of this series using ratio test or comparison test. So so for example, initially we take 2f1, that is Gaussian hypergeometric series. So if we take the ratio, if we just take the limit and you apply the ratio test, and we just get the value mod z. So using ratio test, you can see that if mod z less than 1, then the series converges. Similar way, but this test fails when mod z is equal to 1. So test fails, ratio test fails. So for mod z is equal to 1, we can apply any other test, and if you consider delta is equal to real part of c minus a minus b, and that should be greater than 0. And if you compare these two series, and for mod z equal to 1, using this comparison test, we get 0, it's less than 1. So finally, if A, B, C are neither 0 or negative integer, then 2f1 is convergent in the unit disk mod z less than 1. If either or both of AB is 0 or a negative integer, then the series terminates and the convergence does not enter in the discussion. And if real part of C minus A minus B is positive, then Gaussian hypergeometric series is absolutely convergent on the boundary of the circle. So now what about the convergence of general hypergeometric series or general hypergeometric function? So here we have M and N, M parameters in the numerator and N parameters in the denominator. So if M is less equal to N, then the series converges for all finite Z, and if Z is equal to if M is equal to N plus 1, then the series converges inside the disk, unit disk, and diverges for mod Z outside the unit disk. Now, what is the importance of this hypergeometric series? Most of the well-known orthogonal polynomials and special functions can be expressed in terms of this hypergeometric series or hypergeometric functions. Let us have a look. For example, exponential function, e to the power z. E to the power z can be expressed as on f1 on 1z. Similar way, our other trigonometric functions like cosine z, sine z can also be expressed in terms of hypergeometric function. Similar way, if you take a finite 1 minus z to the power a, then it can also be expressed in terms of hypergeometric function. So there are several things. And if we can express in terms of hypergeometric function, already we know the convergency criteria of hypergeometric function, so that we can easily check the convergency criteria of other functions if it can be expressed in terms of hypergeometric function. Now, let us come to our main topic, that is orthogonal polynomials. So, orthogonal polynomials has some special properties. First of all, orthogonal polynomials can be obtained by applying Gram-Schmidt orthogonalization process. We know about Gram-Schmidt orthogonalization process. It is a well-known procedure to construct orthogonal polynomials or function. Another property is that the orthogonal polynomial of a fixed degree is unique up to a scaling, and a polynomial for p not equal to non-zero polynomial is an orthogonal polynomial if and only the inner product is 0 for any polynomial q with degree q less than p. And this last property can be easily seen from the definition. And a polynomial, non-zero polynomial is orthogonal polynomial if and only p inner product of p and x to the power k is 0 for any k non-zero k any k of degree less than p. So orthogonal polynomial satisfies an interesting property called three-term recurrence relation. So if we have any orthogonal polynomial, then it must satisfy three-term recurrence relation, and vice versa. If we can find a polynomial that satisfies this three-term recurrence relation, we can say that it is orthogonal with respect to some weight function in an interval A. So there are some properties of zeros of orthogonal polynomials. So zeros of orthogonal polynomial Pn are real and distinct. So for n degree polynomial, we have n simple zeros. And it should be noted that there is no common zero between Pnx and Pn minus 1. Last property is known as interlacing property. Between any two zeros of a orthogonal polynomial Pnx, there exists exactly one zero of Pn minus 1. Let us see this with some graphics. So if Pnx is a sequence of orthogonal polynomials on an interval AB with respect to the weight function Wx, then the polynomial Pnx has exactly n real simple zeros in AP. You can see in this. So here we have plotted the 7 degree polynomial. You can see that the 7 zeros are lying inside the interval AB. So this polynomial actually orthogonal in the interval AB with respect to some weight function W. So interlacing of zeros. So if Pn is a sequence of orthogonal polynomial on AD with respect to the weight function Wx, then the zeros of Pnx and Pn plus 1 separate each other. That means you can see we have two colors here. One is in green, another is in red. So we can see that between two green points there is exactly one red point. So actually what happened here, we have checked the orthogonality interlacing property of 6 degree polynomial. So suppose this is a 6 degree polynomial has 6 zeros. So these 6 zeros are plotted here and here 5 zeros. So we can see that between two zeros of 6 degree polynomial exactly one zero of 5 degree polynomial is there. So this property is known as interlacing of zeros of orthogonal polynomials. So now we'll discuss about classical orthogonal polynomials. So to discuss about classical orthogonal polynomials, so let us consider the second order linear differential equation. So this differential equation actually is known as Sturm-Liouville differential equation. Here sigma x is at most quadratic, tau x is at most linear. So where sigma x is actually, that's why I wrote it as ax square plus bx plus c at most quadratic, and tau x is linear, that is gx plus e, are polynomials and independent of n, and lambda n is equal to n into n minus 1 a plus nd, and lambda n is known as the eigenvalue parameter which depends on n, and a b c d e are real parameters. So in the self-adjoint form of this differential equation, the general weight function is given by ws is equal to e to the power integral over ds plus e by ax square plus bx plus c with respect to dx. So the parameters d and e in equation 2 depend on three independent parameters a, b, c. So the parameters d and e depend on the three independent parameters a, b, and c. So automatically we'll have exactly 6 solutions of equation 1. And so here we have 3 parameters, here we have 2 parameters, and this 2 depend on 3. So we have 6 solutions. So we'll have exactly 6 solutions of the differential equation 1. And I told already that this differential equation is known as Sturm-Liouville differential equation, and the 6 solutions are known as classical orthogonal polynomials. And these classical orthogonal polynomials, first 3 classical orthogonal polynomials are Jacobi, Laguerre, and Hermite. You can see the photos of Jacobi, Laguerre, and Hermite respectively. So we have a table here that depending on the value of sigma x and tau x and the weight function, we have the corresponding orthogonal polynomial, and these polynomials are nothing but the solutions of this Sturm-Liouville differential equation using Frobenius method. So we can see that for Jacobi polynomial, sigma x is equal to 1 minus x square, and Laguerre is x, and Hermite is 1. So these are mainly well-known, Jacobi, Laguerre, Hermite are well-known classical orthogonal polynomials. Later on, Romanowski defined another 3 classes of orthogonal polynomials that is known as Romanowski polynomials, and you can see that R Jacobi, R Hermite, and R Laguerre here, with where sigma x is x into 1 minus x and so on. But there are alternative names for Romanowski polynomials. These polynomials are known as finite class of orthogonal polynomials. Now question is that initially when we saw the tree of orthogonal polynomials, we saw that classical orthogonal polynomials has 2 parts, that one is finite, another is infinite. So infinite case we are saying it is Jacobi, Laguerre, Hermite, and finite case we are saying that first class, second class, third class. But question is that why are we calling this as finite also? Because you can see here, for infinite class of classical orthogonal polynomial, there is no restriction on the degree of polynomial. You can see here, this Jacobi, Laguerre, and Hermite are orthogonal with respect to weight function, but here there is no restriction on n. But for the case of finite class, that R Jacobi, R Laguerre, and R Hermite, we can see that p greater than 2 into maximum of n plus 1. That means n is bounded above. Same thing holds for second class also. Here we can see that n has upper bound because p and q are fixed. So for the case of first class, second class, or third class, orthogonality relation will be satisfied only up to a finite sequence, finite terms, or finite degree. After finite degree, orthogonality property will not be satisfied. So although we have infinite collection of sequence of polynomials p and x, for infinite case, it will satisfy orthogonality property will satisfy for all n, but for finite class of orthogonal polynomials, that is first class, second class, and third class, orthogonality relation will be satisfied only up to a fixed degree. After that, the orthogonality property will not be satisfied. It will be just a polynomial. So that's why it is known as finite class of orthogonal polynomials. So, some characterization of classical orthogonal polynomials. So, orthogonal polynomials satisfies some properties, and these properties are common to all the orthogonal polynomials. So, if Pn is an orthogonal polynomial, or Pn is a class of orthogonal polynomial, then its derivative is also an orthogonal polynomial. And it has very wide application, the derivative. We'll discuss in this talk in a later stage regarding the derivative of orthogonal polynomials. So another property, common property, we have already seen that after we are getting classical orthogonal polynomial after solving the Sturm-Liouville differential equation. So every classical orthogonal polynomial satisfies Sturm-Liouville differential equation. And here Ax is at most quadratic, Bx at most linear. And every classical orthogonal polynomial satisfies Rodrigues formula. And derivative of classical orthogonal polynomials are also classical orthogonal polynomials. So there are some remarks that any system of orthogonal polynomials having the above first three properties can be reduced to a system of classical orthogonal polynomials. So we have considered the Sturm-Liouville differential equation. So these are general boundary condition for Sturm-Liouville differential equation. So one can use the Dirichlet condition or Neumann condition for this Sturm-Liouville differential equation. So Jacobi-like polynomials or R-Jacobi polynomials, for the case of this polynomial, A is actually quadratic, B is linear, and A has two distinct real roots. The roots of A lies strictly between the roots of A, and the leading terms of A are between having the same sign. So there are some characteristics. I'm just skipping this. So SL stands for Sturm-Liouville. So the characteristic of Sturm-Liouville differential equation. So the interval of orthogonality is bounded by whatever root Ax has, and the root of Bx is inside the interval of orthogonality. Now question is that how to get the, suppose we know on Sturm-Liouville differential equation. Now question is that can we get a weight function for an orthogonal polynomial? Yes, answer is yes. That suppose that Rx is equal to e to the power integral over Bx upon Ax, then the polynomials Pn are orthogonal under the weight function W is equal to Rx upon X. So if we know the Sturm-Liouville differential equation, from there we can get the corresponding weight function for the orthogonal polynomial. And this weight function has certain properties. The weight function Wx has no zeros or infinities inside the interval, though it may have zeros or infinities at the endpoints. And Wx gives a finite inner product to any polynomial. Another property is that weight function can be made to be greater than 0 in the interval negative, enter the differential equation if necessary, so that Ax greater than 0 inside the interval. Now we discuss about some special orthogonal polynomials. First we consider like Jacobi polynomial. So this is called Jacobi, and Jacob is mainly known for Jacobi polynomial, Jacobi elliptic function, Jacobi simple, and Jacobi operator. So Jacobi polynomials are hypergeometric polynomials or classical polynomials because these polynomials can be expressed in terms of hypergeometric functions. So Jacobi polynomials are orthogonal with respect to the weight function 1 minus x to the power alpha and 1 plus x to the power beta in the interval -1 plus 1. And if this is a standard notation for Jacobi polynomial, that's Pn alpha beta, this is standard notation. And Jacobi polynomial satisfies this differential equation. So if we solve this differential equation using Frobenius method, we get Jacobi polynomial, and we can express Jacobi polynomial in terms of hypergeometric function also, or Gaussian hypergeometric function. But one point should be noted here regarding the convergence of this hypergeometric expression, because we have already proved that if we have a Gaussian hypergeometric series, then it will converge if mod z is less than 1. So in the place of mod z, we have 1 minus mod z by 2. So this will converge if mod of 1 minus z upon 2 less than 1. So this expression is valid inside the analysis 1 less than mod z less than 3. So this is the expression of Jacobi polynomial in terms of hypergeometric function. And generally, a hypergeometric function is an infinite series, but you keep in mind that first parameter is minus n. So whenever you are putting negative integer after certain parameters or after certain terms, the remaining terms will vanish. So that's why it will, from the infinite series, it will be converted into a polynomial. So this expression is valid inside the analysis. So there is an alternative expression of this Jacobi polynomial. This can be, so ultimately when you solve this differential equation, you will get a solution like this. So this is another alternative representation of this Jacobi polynomial, and this is a special case. So Jacobi polynomial satisfies this orthogonality relation. We can see here weight function is there, and interval of orthogonality is -1 plus 1. But keep it in mind that alpha and beta should be greater than -1. Otherwise, this orthogonality relation will not be satisfied. So there is the symmetrical relation that Pn alpha beta x is equal to Pn beta alpha minus x. This is called symmetry, and Pn beta alpha minus 1 is equal to -1 to the power n plus 1 C n. So this is called derivative formula. So if we find the kth order derivative of Jacobi polynomial, then we get this recurrence relation. Now, one special property of classical orthogonal polynomial is that it satisfies 3-term recurrence relation, and it is due to the Faber's theorem we have already discussed. It has a huge application and wide application. We'll discuss it. So Jacobi polynomial satisfies this 3-term recurrence relation, and this is the graph of Jacobi polynomial. It's for a particular parameter and particular case, Pn alpha beta. Actually, by mistake, I wrote 5 just in the prefix. So it's a 5-degree polynomial with alpha is equal to -half and beta is equal to -half. So you can see that the zeros lies between. You can see here 5 zeros. 1, 2, 3, 4, 5, and all the zeros lies in the interval -1 plus 1. And this is the classical theorem of interlacing property. The zeros of Pn, where Pn is an orthogonal polynomial over the interval AB, are real and distinct and lie over the interval AB. That actually we saw. Whatever zero that n-degree polynomial has, it will lie inside the interval -1 plus 1. Now, this is nothing but interlacing properties. So this is zeros for n degree polynomial. This is 0 for n minus 1 degree polynomial. Then it will satisfy interlacing property. And this is called monotonicity property. So if alpha greater than -1, beta greater than -1, and xk are the zeros of Pn alpha beta Jacobi polynomial, then derivative of xk with respect to alpha is less than 0, and derivative with respect to beta is greater than 0 for each k. Now, another different kind of interlacing property of Jacobi polynomial. So this I'm just discussing it, that if alpha greater than -1 and beta greater than -1 and t lies between 0 and 2, then with these properties, then -1, then between -1 and +1, this kind of interlacing property will be satisfied. But I have a question here, that will all the time or all the cases, if we consider if we consider all the cases for the parameter, then will that interlacing property be satisfied? So we'll discuss regarding that. So here we can see that interlacing property fails. So why interlacing property fails here? Because you can see that we have just changed the parameter. Here we have Jacobi polynomial Pn with parameter alpha beta, and here n minus 1 degree polynomial with parameter alpha plus 2.1. I have just changed the parameter and I kept all other things same. Then we can see that here for 4 degree Jacobi polynomial there are 4 roots, and for 3 degree Jacobi polynomial there are 3 roots, but we cannot find one root exactly between 2 roots of 4 degree Jacobi polynomial. So if we change the parameters of Jacobi polynomial, then interlacing property may not be satisfied. So for satisfying interlacing property, Jacobi alpha and beta must satisfy certain properties, and this can be found in these results. So here interlacing property fails. So similar way, different kinds of results are available, like zeros regarding the interlacing of zeros of Jacobi polynomials. So one another property is that when the zeros are interlacing, they are also monotone. But the converse, what about the converse? So therefore the properties hold for the zeros of Pn alpha beta and Pn alpha plus k. But we note that if we take n is equal to 4 and this different kind of parameters, then the Jacobi polynomials, this Jacobi polynomial has these 4 zeros, while this has this also has 4 zeros. But here these polynomials satisfy zeros satisfy monotonicity property, but they do not interlace. So I'm just skipping these things because we have discussed a lot about this monotonicity and interlacing. Let us consider another polynomial. This is a very famous polynomial, and it has very wide application in non-linear optimization. So if we take alpha is equal to beta is equal to -half in Jacobi polynomial, then Jacobi polynomial will reduce this to Chebyshev polynomial. Some people used to write t also in the spelling of Chebyshev. We are just writing it in Chebyshev. So Chebyshev polynomial can be defined like this, and this satisfies these 3 term reconciliations. And this is the graph of Chebyshev polynomial. I have just used a different notation Tn. This is the standard notation actually for Chebyshev Tn. Since we are using this spelling Chebyshev, that's why it is Tn here. And you can see that here you have used this spelling Che. That's why we have used C notation C. So it depends. So this is the graph of Chebyshev polynomial. So according to the property of orthogonal polynomial, we can see that all the zeros lies between -1 and the +1 in the open interval, and this polynomial satisfies interlacing property. For example, you take n is equal to 1. So this is that 45 degree angle, this line. And if you take n is equal to 2, we have which one? This polynomial. This is my mouse pointer. So we can see that exactly 1 zeros between the, otherwise you just take n is equal to 2 and 3, so it will be visible for you, n is equal to 2 and 3. So you can easily check that between two consecutive zeros of higher degree polynomial, exactly 1 zeros of lower degree polynomial exist. So these are some properties of Chebyshev polynomials, and this is the orthogonality relation of Chebyshev polynomial. This is the main thing. That's why Chebyshev polynomial is famous. Chebyshev polynomial are useful for non-linear optimization problem. So this is known as minimax problem. So if you solve this problem, the solution of this problem can be expressed in terms of Chebyshev polynomial. So when people wants least error in non-linear optimization problem, then that time the Chebyshev polynomial will be very useful. So this is Chebyshev polynomial of second kind and can be defined like this, and this polynomial satisfies this orthogonality relation with respect to this weight function 1 minus lambda square root. So this is a generating function for Chebyshev polynomial. Why do we need this generating function? If we compare the coefficient of t to the power n both sides, then we get this second kind Chebyshev polynomial. So this is the graph. The same way we can discuss the zeros, behavior of zeros of ultraspherical Gegenwert or Gegenwert polynomials. So same way we can discuss about Hermite polynomials. So Hermite polynomials also satisfy these properties, and this is Lagrange polynomial. So this is a differential equation of this Lagrange polynomial, and it satisfies this orthogonality relation. This is the generating function of and reconciliation for Lagrange polynomials, and this is the Rodriguez formula. So Rodriguez formula is important because from the Rodriguez formula we can find the weight function of the polynomial and other information. So now we move towards different thing. The application of this orthogonal polynomial, we move towards that. So initially we discussed about, or when we discussed about classical orthogonal polynomial, one property we have discussed that derivative of classical orthogonal polynomials are also classical orthogonal polynomial, and it satisfies all the characteristics of orthogonal polynomials. So but question is that why do we need a derivative of orthogonal polynomial? We consider this is term level differential equation, for example. So this is nothing but first class or ALGEBRA polynomial. It has a regulation number 0 minus 1. So how to solve it, we know. So before solving this differential equation, what we do, we differentiate this differential equation with respect to x k times, where k less than n. You can difference 1 time, 2 times, 3 times, according to your wish. It should be less than the n. Okay. And we denote Zn as dk dxk 1x. Then we apply Frobenius method to this differential equation 12. And applying Frobenius method, we will get solution like this. This Zn minus k is known as the kth derivative of ALGEBRA polynomials. Now, suddenly, it may be a question, why should we study this? We will see that. So this property, if we consider this polynomial Zn minus k, we can see that this Zn minus k after differentiating satisfies orthogonality relation with respect to this weight function. If you put k is equal to 0, you can find the weight function for first order derivative. Similarly, for nth order derivative, you can find. So this is the outline of the proof. I'm skipping it. It's just you just find that adjoint form and the multiply and do some calculation. You will get this result. Now let us see some particular case. Suppose p is equal to 4 not 2 and q is equal to 0. Then we can see that this polynomial satisfies orthogonality relation up to 200 degree. That's why it is called finite. So if you take m n greater than 200, so if I take 201 degree polynomial, it will not satisfy the orthogonality property. That's why it is called finite class. So it is preserving the finite class property, and it has self-adjoint form, and it has Rodriguez formula. So examples, for n is equal to k plus 1, k plus 2, we will get this kind of particular polynomials. You see, 0 degree polynomial 1, this is a first degree polynomial, second degree polynomial. So we can generate this kind of, you can generate your own polynomial using this, like this. So this is a norm square value of this polynomial, and definitely from the norm you can see that it's a L2 norm and say a Hilbert space. So orthogonal polynomial, actually classical orthogonal polynomial, it's a L2 space, and this satisfies this three-term reconciliation also. And this is the generating function for this. So using this generating function also, we can generate this polynomial. So that's why, see, this relation shows that why it's called R-Jacobi polynomial, because this polynomial can be expressed in terms of Jacobi polynomial. So that's why this Ramanujan polynomial is known as R-Jacobi polynomial, because it can be expressed in terms of Jacobi polynomial. So, and this is, since this is classical orthogonal polynomial, so this polynomial can also be expressed in terms of hypergeometric function, and actually Gaussian hypergeometric function. Now we apply the orthogonal polynomial in Gauss integration theory, or you can say numerical application. So this is a general Gauss quadrature formula. It can be found in any well-known books of numerical analysis. So in Gauss quadrature formula, it's a well-known formula. Here Rn m is the remainder term, and actually it's a remainder term. So what will you do? We'll apply on orthogonal polynomial and check which polynomial gives us better result. So this is just procedure. So we have just applied what we did actually in that remainder term Rn. We have used the weight function of our R-Jacobi polynomial. Actually, this is not R-Jacobi polynomial. This is a k time differentiation of R-Jacobi polynomial. This is the weight function for that. So we are using here this RNF. Now we can see an interesting thing. Here k stands for derivative, the times of derivative. So initially what we did, we have considered Sturm-Liouville differential equation, and we have considered kth order derivative. So actually we have the kth order differential polynomial. So if we take k is equal to 0, that means original polynomial without any differentiation. So if we apply R-Jacobi polynomial without differentiating, our remainder term will be like this: 6.625 into 10 to the power minus 14. This is the error for this particular case, q is equal to 0 and some particular values. But if you differentiate one more time, suppose first time differentiation, then we get 2.55 into 10 to the power minus 17. You can see that errors are decreasing. For second time differentiation, you can see 10 to the power minus 20. For third time differentiation, 10 to the power minus 24. So you increase the number of differentiation, we get the less error. So that's the important. So instead of using the original orthogonal polynomial, if we use the derivative polynomial, we will get less error. So that is the one important application of orthogonal polynomial in approximation theory or numerical analysis. Now my another question is that we have so many polynomials, which polynomial will give you the least error or less error? We have Jacobi polynomial, we have Lagrange polynomial. So here, for example, if we consider R-Jacobi and Jacobi, we see that we have already checked it that the finite class of orthogonal polynomial is to give better result, means less error. So this is one property. So here we have fixed the value of P and where is the value of Q, and here we have, oh, sorry, it's not working. Just pardon, just computer, it's just stuck. Okay. I think it's again started working. Okay, so if you fix P and vary Q, you'll get, again you can see that for increasing the number of times of differentiation, we get less error. So if you are not comfortable with tables, you can see with the graph. Here along x-axis or real axis we have k, the number of times of differentiation. So you increase the number of times of differentiation, you can see the errors are becoming very less. You see the right hand side graph. So we increase the number of differentiation, it gives us less error. So it has some observation that higher order derivatives of general or orthogonal polynomials provides us less error and better results. And instead of orthogonal polynomial, if we apply its derivative, it satisfies orthogonality relation, reconciliation, hypergeometric representation, everything, and numerical. And these orthogonal polynomials and its derivatives are very useful for numerical quadrature and interpolation formula. And it has some interesting properties of errors. Now, before moving towards on real life example, we should know about some basic knowledge, topics about continued fractions, because one thing we know that most of the real life problems can be expressed in terms of differential equations. Most of the problem, not all the problems. And most of the problems are non-linear in nature. So to solve this kind of problems, we need the help of orthogonal polynomials and some special functions. So for that we need continued fractions also. You can see here that root 5 minus 1 by 2, it's irrational number. So we know that if it is a number is irrational, we cannot express in a specific form like P by Q form, we cannot express. So what do we do? So we can write it as 1 by 1 plus root 5 minus 1 by 2. Similar way, we can continue this process. So we can see that root 5 minus 1 by 2 is nothing but 1 by 1 plus 1 by 1 plus in this form. This kind of forms are known as continued fractions. Actually, these are fractions. So fractions are continued. So this ratio is known as golden ratio. This is very important ratio. The solution of x square minus x minus 1 is a positive root. And this is irrational number, but this approximation is rational. Why? Same kind of thing we can see here. See pi 3.14.1592, we cannot find the specific representation, but we can write pi is equal to 3.14, instead of writing like that, 3 plus 1 by 0.141592. Similar way, we proceed to the next line, like 3 plus 1 by 7.0625, like this, and you continue. So when you continue this procedure, we can find this fraction. This is another kind of continued fraction. So this is also, so these continued fractions are infinite continued fraction. So one point to be noted here is that if we have irrational number, then we have infinite continued fraction. Infinite in the sense that it cannot be finite here. We cannot end here. But if instead of irrational number, if we take a rational number, we will always get a finite fraction, finite continued fraction. Now we'll move towards a real life application of orthogonal polynomials. So I'm going to discuss about birth and death process. So birth and death process, to before going to the mathematical structure or mathematical model for that in terms of differential equation, let us see what you mean by birth and death process. So suppose you want to get money from ATM and you are in a queue. So suppose 3 persons are standing there and you are the fourth person to get the money. So it's a queue. So after getting the money from the ATM machine, the first person will go out. So your length of the queue will decrease. We call it death. But meanwhile, new person will come and join the queue. So fourth person will come and join the queue, fifth person will come and join the queue. So in same time, the length of the queue will also increase. This you can call as birth. So similar way, normal population, birth means a newborn baby, death means somebody is dying. So this has very wide application in population dynamics and queuing theory and other research areas and other and it gives solution for various practical problems. So here lambda I denotes the birth rate. So from 0 stage to 1 stage some birth is required. So when some birth occurs, so we call that rate, birth rate as lambda. So after some birth rate, it will go to the next stage, and consequently some death rate, after some death, it can come to the previous stage. So we can call it as death. And actually this was the linear structure, but in real life, birth, death structure may be looking like this, complicated, and this is general birth and death. Qualities are constant over time. So these are some special cases of Markov process, and for birth and death, we are the transitions. Transition means one stage to another stage. So that is limited to only birth and death. So these are some increasing changes. So suppose death is suppose birth is occurring more, so we can call that birth rate is increasing like that. So I'm not going in detail in this. Just I'm going to the main equation. So any birth and death process satisfies generally birth and death process with lambda, with birth rate lambda and death rate mu satisfies this kind of differential equations, and this differential equation is known as Kolmogorov differential equation. People also call it Chapman-Kolmogorov differential equation. So now question is that how to solve this kind of differential equation. So this is very difficult question, and it's not easy to solve this differential equation. So and till now simple and solution for this differential equation or simple answer is not there. So what people used to do is that apply method of separation of variables. We know the method of separation of variables. So you just take Pij t is equal to ft qij qfj, and you apply method of separation of variables, and after certain calculations, so whatever I'm doing, I'm just telling about the first block, the first set of equations. So if we apply method of separation of variables in the first set of equations, you will get f dash t upon ft is equal to something. We call it minus x. So ultimately you will get ft is equal to e to the power minus xt in this form. I'm hiding some calculations. These calculations are available in a book of orthogonal polynomials. I do not want to discuss the full calculation. So if you just proceed with method of separation of variables, then you can see that we'll find a three-term reconciliation in terms of capital F. What is capital F? That is used in the method of separation of variables. But problem is that this capital F is not a polynomial. May be polynomial, may not be polynomial. So and the final solution using separation of variables may be obtained like this, and the full calculation and all the details are available in the book of Ismail, Classical and Quantum and Orthogonal Polynomials. If anybody is interested, they can see the proof in this book. So my aim is not to prove this result. My aim is to consider this three-term reconciliation. So in the place of fn, if we consider a function pnx is equal to minus 1 to the power n and product of mu n, where mu n are death rates, and multiplied by fn, then we get a three-term reconciliation like this. Our main target was this only, because we know that according to Faber's theorem, if it is a classical orthogonal polynomial, then it will satisfy three-term reconciliation, and if it is satisfying three-term reconciliation, then definitely it will be orthogonal with respect to some weight function. Now we can see that Pnx satisfies three-term reconciliation. So that means definitely this will provide us a classical orthogonal polynomials. Generally, these orthogonal polynomials are known as birth and death process orthogonal polynomials. So you can see that alpha n is equal to lambda n plus mu n. Here, where lambda n are birth rate, mu n are death rates. Same way, beta n is here lambda n minus 1 into mu n. So this three-term reconciliation is combined of birth rate and death rate of a system. So if we know birth rate and death rate, we can construct orthogonal polynomials. So that may lead to a solution of a real life problem. So if you know lambda and mu, that means birth rate and death rate, you put the value here, we will get Pn, so it will provide us some orthogonal polynomial with respect to some weight function. So how to get? The simplest example or cases of birth and death process are linear cases. So every classical orthogonal polynomials are birth and death process polynomial, because every classical orthogonal polynomial satisfies three-term reconciliation. For a simple example, if we take birth rate equal to lambda n plus 1 and death rate is equal to n plus alpha, then it provides us Lagrange polynomial. Means Lagrange polynomials are birth and death polynomials with respect to lambda n and with respect to this birth rate and death rate. And we already know the weight function for Lagrange polynomial. Similar way, some constant multiplication of Lagrange polynomial can be obtained for this kind of birth rate and death rates. Zeros, so already we know that the zeros of orthogonal polynomials lie inside the interval of orthogonality. So the zeros of birth and death process polynomials belong to 0 infinity. So now we had this system of differential equation and we were unable to solve it. So another alternative approach people used to apply is Laplace transformation. Generally we apply when we are unable to solve some problems. So if we take Laplace transformation to the transition probability, so transition probability means going from one stage to another stage. So then we can see that the Laplace transformation of this transition probability can be expressed in terms of continued fraction. That's why we have discussed the continued fraction. So this kind of continued fractions are known as S fraction. Now, one question may come into our mind that we have simple series expansion. Why should someone consider this kind of big continued fraction expansion? Main reason is that the rate of convergence is very higher than the series. And sometimes if the formal power series does not converge, that time we can apply continued fractions to get some approximated value. So these are some special cases with another. So it is difficult to write continued fraction like in this form. So in that case, we can use this kind of symbols for continued fraction. Now, the remaining thing is that we have this continued fraction. Is it possible to express in terms of simple form like P by Q form or rational approximation? Answer is yes. We can express in the form of AKS by BK. So this is actually K time K fraction. But if we have infinite fraction, then also we can express the continued fraction in terms of A by B. And using Wallis formula, we can compute. So these are some special mathematical models. So if you consider some real life problem where birth rate plus death rate is equal to 1 and this is equal to q to the power n, then you can see that this can be expressed in terms of Ramanujan continued fraction. So that after applying some inverse Laplace transformation or different kind of properties, we can get the solution. Similar way, you can see that hypergeometric function also can be expressed in terms of continued fractions. And these are some corresponding birth and death rates. Similar way, suppose these kind of sequences are known as chain sequences. So if we have birth and death in this form, then we can find a continued fraction like this and we can handle the situation. So main thing is these are tools to solve some problems. It may not give us a direct solution, but it will be useful to solve other problems, because ratio of hypergeometric functions or hypergeometric functions are useful to express other functions, or special functions or polynomials. So this is an interesting property of continued fraction, that 1 by 1 plus z can be expressed in the product of two continued fractions. And these are the corresponding birth and death rates for this corresponding process. Similar way, this can also be done, and these are the corresponding birth and death rates. And one can see the book of H.S. Wall, Theory of Continued Fractions, to get these ideas. So relation between these two BDPs. So suppose you have lambda n and lambda n does two different kind of BDP, birth and death rates. So these properties are satisfied. So to know about orthogonal polynomials, continued fractions, and related things and special function, one can see the book of Andrews Askew Roy. This book may be useful, very useful for special functions. But if you are interested to read about orthogonal polynomials, then the book of Chiara will be much useful for you. And book of Ismail will provide applications and information of different kind of polynomials. And the similar books are there for Renville, Time, and main book, the continued fraction is H.S. Wall. So one can use the book of H.S. Wall for the theory of continued fractions. Thank you very much. Stay safe, stay home.
Am I audible?
Yes, yes.
Okay. Sir, thank you very much. We are ever grateful to you for your remarkable speech. It is very informative and very well represented. It will surely add excellence to the knowledge base of our audience, and it will surely fulfill our goal. So now I have some questions which
Yes.
I have already put in the chat box. Two of them I have received from the YouTube audience. One question is asked by Nirvik Marshanto, who is asking that why we introduce such weight functions, what is the need of such functions, and another is by Subhash Mondol. And Mr. Anish Kumar has also put two questions here. So, sir, if you please go through these four questions. And
I'm sorry for interrupting. Can you ask me the question one by one, please? So it will be easy for me to understand and answer. But one by one, please.
Okay. First question is asked by Nirvik Marshanto, who is asking that why do we introduce such weight functions? What is the need of such functions?
Weight function.
Weight functions. Why
Okay.
do we introduce weight functions?
Okay. Without weight function, that orthogonality relation will not be satisfied. That's the main reason. Another thing, you can see that the inner product is defined. Okay, I'll go to the main slide so that it will be easy for us to discuss that. Yes. So you can see that inner product of Pn and Pm is there. So here, if you do not use the weight function, then your integration may not exist somewhere. Sometimes this orthogonality property may not exist. another thing is that when you see this property. Gram-Schmidt orthogonal. When we apply Gram-Schmidt orthogonal test, that time we have to apply inner product, and to define the inner product, weight function is very much required. Otherwise, what weight function plays role here is that WX, PNX, PMX, PX is there. So mainly, actually, orthogonality relation is defined as integration A to B, PNX, PMX, B of mu x, where mu x is positive Borel measure, and mu is, if mu is absolutely continuous, then B of mu x can be expressed as Wx dx, so that you can integrate it. So without a weight function, it may violate the Riemann integration theory, I think.
Okay, sir. Next question is asked by Subhash Mondol, who is asking that is there any general method for solving any type of second order Sturm-Liouville equation?
Okay, actually, this Sturm-Liouville equation is a differential equation with variable coefficient. So best way is that to apply series solution method. First, you have to check whether your point is ordinary point or not. If the point is ordinary point, then you apply series solution. Otherwise, you have to check whether the point is regular singular point or not. If the point is regular singular point, then you apply Frobenius method. And if your point is not a regular singular point, you can modify that Frobenius method, you can solve. Otherwise, this is the standard procedure for solving differential equation with variable coefficients. More than that, if you are interested, you can use conjugate fractions also, but that is generally not in the syllabus of the UG or PG course. But this is the standard procedure for solving this Sturm-Liouville equation.
Okay, sir. In the meantime, we have got reply from Nirvik Mashanto. He says in the YouTube chat box that he has understood your answer and he's quite okay with that. Now, Anish Kumar has asked you that with respect to which function here we checking error after differentiating classical orthogonal polynomial.
Can you please repeat it?
Yeah, I'm repeating this again. With respect to which function here we are checking error after differentiating classical orthogonal polynomial.
With respect to which function means, okay, generally what happened here, I'll tell you. I understand the question. Actually, we have the Sturm-Liouville differential equation and we are differentiating with the, I just show you for a minute, please. Where I'll show that. X what we did is we have differentiated with respect to and we with xk times and we got like that. But when you are approximating, so this is the solution after using Frobenius method. So this is orthogonal with respect to this weight function. So actually we have used this weight function for approximation problem. You can see here. You can see here we have used that same weight for approximation. Okay. Actually differentiated with respect to x itself. Okay. Any further questions?
There is another question which is also asked by Anish Kumar.
Yeah.
How orthogonal polynomial and continued fraction relating with each other? How orthogonal polynomial and continued fraction are related with each other?
Interesting question, and I think that this is the best question I feel because it's a very important. You see, then for this, what we should go to the three-term reconciliation. You can always rearrange three-term reconciliation in terms of continued fraction, and that will lead to some G fraction, that is a special type of continued fraction which is used for birth and death process and this kind of thing. So for example, here on 3-term reconciliation is there. Where is that? Okay, I'll show that. I think somewhere it is there. Okay. For example, this is the 3-term reconciliation. You can rearrange this 3-term reconciliation how we did it for pi or other function, other values. So you can rearrange in such a way that it can be expressed in terms of continued fraction. So from 3-term reconciliation of orthogonal polynomial, we can always generate a continued fraction, and that has wide application, especially in Markov process and Bartel method. Okay. Next. I am unable to hear. I am unable to hear them. Sir, I am unable to hear.
Am I audible?
Okay. Yeah, now you are audible. Yes.
Okay. Anish Kumar has replied that he has got his answer. Now I will ask Dr. Abhijit Banerjee, my co-convener, to moderate further this question and answer session, and also to host the next session of today's program. Abhijita, if you have any further question, please proceed.
Sir, pardon, sir. Can you repeat, please, sir? Yes. Yeah. Yeah. Okay, there are several. So Nikifor actually book is also there. Are you talking about the book or method? Okay, so yeah, several methods are there. Like continued fraction method and Nikifor books methods are there. So for that method, I did not mention here, but for them I can just suggest some reference here. Just 1 second, I'll say it. In my last slide, I just suggest there to see the book of Renville and book of NMT. There in that books there are several methods available. They can apply it. No, actually, for this kind of we generally use method of what you call that Frobenius method itself, standard method. That is actually particular cases methods. So some continued fraction methods are also available. So it depends on the problem actually, because sometimes you know that solving differential equation is not easy. So it depends on the equation. So it depends on the situation, we have to apply the method. So sometimes maybe the Nikifor method may be useful. Sometimes maybe series solution method may be useful. So it depends on the particular problem.
Hello.
Yes, you are. Yes, you are.
Yes, sir. Yeah. Okay. Am I audible? Okay. First of all, I am thankful to the Department of Mathematics, Gorbeta College, for giving me this opportunity. And I am especially thankful to Dr. Abhijit Banerjee sir for his inspiration to give this kind of lecture. Okay. Is my slide is visible? Is the slide is visible?
No, sir, not. So actually, you have to present your slide, I guess. Yes, now it is visible.
Yeah, actually some network problem is there here today. Little problem. Okay. Actually, this is a classroom lecture and especially for UG students. Okay. And the aim of this lecture is to inspire the UG students to visualize some mathematical ideas. Okay. Okay. Actually, that title is actually visual proofs of some well-known results. We have seen many results in our undergraduate text, and here we try to give some visualization of them. Okay. First, I say what is visual proofs or what is proof without words. Of course, proof without words are not really proofs. Generally, proof without words are pictures or diagrams that help readers to visualize why a particular mathematical statement may be true, or also to see how one might begin to go about proving it true. Actually, we teachers must try to develop the ability to visualize mathematics in our students. Of course, many times it needs some words to explain, so it is not always without words. In this presentation, we will present some elegant visual demonstrations of certain mathematical ideas which you will enjoy. Okay. First, we present some visual demonstration of mathematical identities. Okay. I think my slide is not visible. Slide is not visible. Why? Is it? No, slide is not changing. Why?
Sir,
Just
if you don't have any problem, then you can mail this to me or Obhijit Da, and we can scroll it down, and you will describe the slides if you face
Yeah,
any
that is better.
problem regarding
That is better.
this.
Yeah, just a minute. I mean, just a minute. Just a minute. I mail you. Okay, I email you in to Dr. Rajlakshmi. Okay, I email you.
Okay, you have mailed me to ju.rajlakshmi, no?
Yeah. From that mail, I get the schedule, etc.
Okay. One sec, let me open that. Please give me 1 sec. I'm going to arrange.
But in between time, I need to write something. So how it is possible?
Excuse me?
Actually, when I am presenting the slide, as well as I want to write something in desktop. So is it possible?
Actually, okay, sir. You proceed with your presentation. If
Okay.
you face any problem again, then I will start presenting from here. But
Okay.
I mean, simultaneously writing, actually, I don't think it is possible for me. Actually, you start, we'll
Okay.
manage.
Okay. No problem. Okay. So first, I want to present a very famous identity. Okay, that is the sum of first n natural numbers is n into n plus 1 by 2. Okay, and this is very famous, and we know it from our 12th standards, right? So if I ask you to prove this identity, basically what you do, you do some principle of mathematical induction. You apply principle of mathematical induction and you prove this. Okay, but here we give some visual presentation of this identity. Okay. Okay. So for that, we first need to introduce one idea. So first, I ask you one question. So what is the area of a unit square? Just a minute. If I take a unit square, no problem. Just a minute. Just a minute to talk. Just a minute. Just a minute. Actually, from morning, and then some network problem is going on here.
Yeah, it's okay. You take your time, no problem.
Okay. So first we demonstrate that the sum of first n natural numbers is n multiplied by n plus 1 by 2. Okay. For that we need one thing. First we consider a unit square, 1 unit square. Okay. 1 unit square. So what is the area of that? That area is actually 1. And one thing I ask here, can you prove this, that the area of a unit square is 1? This is my question to you, student. Actually, this is an axiom that that the area of a unit square is 1. Okay. So I just mentioned it. Okay, and here we always mean that 1 means the area of a unit square. Okay. So naturally, what is the meaning of 2 here? So meaning of 2 is actually 2 multiplied by 1. That means here we add 2 unit square side by side. Okay. So here the meaning of 2 to us is sum of 2 unit square. Okay. So here look, 1 means 1 unit square, then 2 means 2 unit square, then 3 means 3 square, and then 4 means 4 unit square, and so on. 5 means 5 unit square, 6 means 6 unit square, and 7 means 7 unit square. Okay. So we just put all the squares in this way, right? And then we join this point by a line segment. Okay. So by this we have one big triangle. Just you see that we have one big triangle and some smaller triangles. Right? Here you see that here 7 smaller triangles are there. Okay, because we consider 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. So here we have one big triangle and 7 smaller triangle. Okay. Now what is the area of this bigger triangle? The area of the bigger triangle is the height 7. Okay, and the base is 7. Okay, so the area is actually half multiplied by 7 into 7. Okay, and what is the area of the smaller 7 smaller triangle? Look, the length is 1 and the height is 1. So area is actually half into 1 into 1. So here this figure represent that the sum of first 7 natural number is actually half into 7 plus 7 into half into 1 into 1, right? So just to take half 7 by 2 outside of that, so you have 7 plus 1. Okay. So if you just apply this process up to n times, before starting this lecture, I have already mentioned that proof without words or visuals are not actual proofs. Okay. So this is the actual kind of visualization. Okay. So just we just apply this method up to n, right? First n natural numbers. So just if you do the same process up to n natural numbers, so you have 7 is replaced by n. Okay. So actually the sum of first n natural numbers is n multiplied by n plus 1 by 2. Okay. So this is the visualization that the sum of first n natural numbers is n multiplied by n plus 1 by 2. And this proof is given by I. Richards. Okay. Okay. The next identity is this is again another well-known identity in our undergraduate class, that is the sum of the square of first n natural number is n multiplied by n plus 1 multiplied by 2n plus 1 divided by 6. Okay, so we have give another visualization for this identity. Okay.
Sir, one thing I'm going to interrupt you. Actually,
Yes.
In YouTube, the audience are telling that if you kindly Control L, press Control L, enlarge your screen, then it will be much more visible in YouTube.
Yeah, I know it, but I am controlling two things. One is my PDF, and another is writing pad. So it is difficult actually.
Okay, sir, no problem. Continue.
Okay. So now I am going to present the another identity. This is very famous, and if I ask you the proof of this identity, then again you go for and you apply principle of mathematical induction. Yes, that kind of identity has another proof. There are probabilistic proof. Okay, but the easiest proof that is application of principle of mathematical induction. But here we give another visualization of this identity. Okay. Just see here again. I have already mentioned that 1 means the area of a unit square. Okay. Just a minute. And so what is 1 square? Just that 1 square means actually in my lecture, area of a unit square. Okay, so what is 2 square? So 2 square is actually 4 into 1. So actually this is actually 4 unit square. So this is a block of 4 unit square. Okay, and similarly, what is 3 square? 3 square, this is actually 9 into multiplied by 1, right? So this is actually block of 9 unit square. Okay, so see this figure. So this is actually 1. Okay, this is 1 square actually, and that portion is 2 square. Just count it 1, 2, 3, 4. So for 2 square, then go to the violet blocks 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is actually 3 square. Okay, then 1, 2, 3, 4, and 5, 6, and up to 16. So this block represents 4 square, and again this green block represent 5 square. Actually here we consider up to 5 square, 1 square plus 2 square plus 3 square plus 4 square plus 5 square. You can just proceed by this way. Okay, so we add them, 1 square plus 2 square plus up to 5 square. So if we add them, so we have a blocks of unit square. So this is the block. So this is the block of those number of unit square. Okay, so now we just rearrange this block in another way. Okay, you look at the this block, the green blocks. Here you have 1, 2, 3, 4, 5 rows, right? In each row you have 5 blocks. Okay, so you have 5 rows in that bigger blocks. Okay, so you just break the bigger square into 5 different parts. So first row, this is the second row, this is the third row, this is the fourth row, and this is the fifth row. So you have in that block you have 5 rows, right? So you just break them into 5 parts. This one the first, the second, third, fourth, fifth. Okay. Now look at the another that block. In that block you have 4 rows, 1, 2, 3, 4, right? And now you break that block into 4 parts and put them in the previous one, right? So by this way, so this is the first block, second block, third block, fourth block. Okay, now you consider that the block violet blocks. Okay, here you have 3 rows, right? And you break it into 3 parts. So this is the first one, second one, third one. Okay, now you consider this block. Here you have 2 rows, you break into 2 parts, the first one, second one. Okay, and finally you have the single block, just you put here. So this block can be written as sum of 1, 2, 3, 4, 5 blocks. So you you consider this block and you just partition that block into 5 parts. So you have 5 blocks. Okay. Now you take next step is that you take the 2 copies of this block. Okay, you take 2 copies of this block. So you have this block 2 times, this block 2 times, this block 2 times, this block 2 times, and finally this block times. Okay, so you consider the double of this block. So you glue those blocks. So you considering double of these blocks. So you just glue them. Just look here you have 2 blocks. Just look at this one. So you have this block and you just rotate that one and add. So you have a square. Okay, and then you take this block twice and add in this way, right? Again you take this block twice and add. Again this you take this block, you add, you have a rectangle, and you take this block twice and join them side by side. So if we consider this block twice, so we have new 5 blocks in this way. Okay, now you consider 3 times of this block. So 3 times of this block means this block and 5 those blocks. Okay, so these blocks means 1 times and these blocks are 2 times. So you add those all blocks together. So this is the 3 times. Just you look this figure. Just you look this figure. So this is the first block. This is S, right? Then you put this block here, and upon that you put this block, and on that you put this block, and upon that you put this block, and finally you put this block here. So if you arrange these blocks are in this way, you have a nice rectangle. Okay. Now look at the rectangle. What is the length of this rectangle? You see that 1 plus 1, 2. Here 1 plus 1 plus 1, 3. So this is 1 plus 2 plus 3 plus 4 plus 5. So if you apply this process up to n, so the length of this block is actually 1 plus 2 plus 3 plus up to n. Okay, so 1 plus 2 plus up to n. And what is the base of this block? So this is actually 1, 2, 3, 4, 5. So 5 plus 1, 2, 3, 4, 5, 5. So 5 plus 5 plus 1. So 2 into 5 plus 1. Okay, so if you apply it for up to n, so this is actually n plus 1. So this is actually n plus 1. Okay. So what is this block? This is the 3 times of this block. So the sum is actually 3 times of that block 3s, and 3s is actually what is the area of a rectangle? Length into breadth. So length is 1 plus 2 plus up to n, and breadth is 2n plus 1. So what is s? Just to add, just this simple calculation. This is actually n into n plus 1 by 2, and this is actually 2n plus 1. So actually s equal to n into n plus 1 into 2n plus 1 by 6. Okay, so now you can ask me a question that why should I do this kind of juggling or puzzling? The actual thing is that if you apply principle of mathematical induction, that proof is very easy. But this is a visualization. This is you can see that here is no words. If I don't explain anything, just one picture is there, and that picture tells that this picture, these blocks tells that this is nothing but sum of square of first n natural numbers is n into n plus 1 into 2n plus 1 by 6. Okay, so that is the beauty behind that thing. Okay, and this is the paper written by me. This is my first paper on this area, and this paper is published in Mathematical Intelligence, and later it is republished in Scientific American. Okay. So next, okay. Next, I show another identity, and that is also known to you, that q of first n natural number is n into n plus 1 by 2 or whole square. Okay, so this is another identity, and it is very well known to you, and this identity has several different kind of proofs. One easy proof is again using principle of mathematical induction, and another proof is available, that is using probability. Okay, but here again, here we give a visualization of this proof. Okay. Okay. Give another visualization. Okay. Again, here we consider one cube. So what is we can think one cube as 1 into 1 square. Okay. Again, we can think 2 cube as 2 into 2 square. Okay. Also, so 1 cube means we are going to consider 1 unit square. Okay. So 2 cube means we are going to 2 blocks. Each block contains 4 unit square. So this is this is actually, we have discussed that this is actually 2 square. So 2 square plus 2 square is 2 cube. So 2 cube means 2 into 2 square, and similarly 3 cube means 3 cube. Similarly 3 cube means 3 into 3 square. So we are considering 3 blocks, and each block contains 9 unit square. Okay. Now you look at the figure. They first consider 1 unit square. So this is actually 1 cube. Okay. Then they consider so this is actually 1 2 3 4 2 square. So we can think as this square, this block as sum of these 2 blocks. Okay, so 4 blocks can be think as sum of 2 plus 2 blocks. So we place so this is 1 block, and we just divide 1 block into 2 parts and place it here, right? Place it here. So actually this part actually to us 2 cube. Okay. Now just look at the figure. So this is actually 1 cube, this is actually 2 cube, and next you consider 3 cube. Then you have 3 blocks. Just to place 3 just 3 blocks here like this: 1 block, 2 block, 3 block. Okay. Then you are considering 4 cubes, so you have 4 blocks. So you are considering 4 blocks. This is 1 block, 2 block, this is a 3 block, and you have 1 extra block. That extra block you divide it into 2 parts and place then between this place. Okay, just you repeat this process. If you repeat this process, you have a bigger block. Okay, in that bigger block you have observe that this is again a square. This forms a square, and the side is actually, this is actually 1. Just look, this is actually 2, then this is actually 3, then you just look, this is actually 4, then this is actually 5, this is actually 6, and up to this is actually n. So the sum of the block is actually area of a square whose side is actually 1 plus 2 plus up to n. Okay, so this square, and this is nothing but just we rearrange these blocks. Okay, just we rearrange these blocks. Okay, so the sum of 1 cube plus 2 cube plus up to n cube is nothing but sum square of 1 plus 2 plus n. Okay, so and this is nothing but n into n plus 1 by 2 whole square. Okay, so this is another visualization of our well-known identities, and this is actually established by J. Berilov. Okay, this proof is given by J. Berilov. Okay. Okay. Next, we demonstrate some mathematical inequalities. Okay, we are going to give some mathematical inequalities. The first inequality is arithmetic mean is greater or equal to geometric mean. We have established that one. Okay, and again this proof is very easy. In undergraduate class our teachers do some calculations and established, but here we present a visual proof that the arithmetic mean of two numbers is bigger than geometric mean of that two numbers. Okay, we have to present this one. Okay, so we know that if we consider two real numbers, two positive real numbers, we are considering two positive real numbers. Okay, A and B. So now we draw a rectangle. We draw a rectangle with side A and B. So this is a rectangle. This is a rectangle whose side is, this is A and this is actually B. Okay, now we extend this length. Okay, we extend this line to up to that. So this length is actually A. Okay, and this is B. Just we draw in this way. Oh, sorry, this is A again. Okay, and we extend this length. Yes. So just we draw this figure, right? This is B. This is B. A. Okay, now you see that this is a bigger square. The outer square is a bigger square whose side is actually A plus B, right? And inside there are 5 rectangles, 1, 2, 3, 4, 5. Okay, and this is a rectangle. The area of that rectangle is actually AB. Okay, again area of that rectangle is again AB, and this is again rectangle. Area of this rectangle is AB. And area of this rectangle is AB. Okay, so now question, what is the area of this square? So obviously the area of this square is actually A plus B whole square minus 4B, and from figure this is positive. You see that it occupies some area, right? So since it is an area, so you know that is again axiom. The area cannot be negative. That is again axiom. So this must be positive, and this is nothing. This is actually nothing but A plus B by 2 whole square. So this is actually greater or equal to square root of B. So this is the visualization that arithmetic mean is greater or equal to geometric mean of two numbers. There are several proofs that arithmetic mean greater or equal to geometric mean greater or equal to harmonic mean. There are several visualization. At least 10-15 visualizations are there, but we are not going there. Okay, just here we demonstrate one. Okay, next we discuss another inequality. Okay, that is sine function is subadditive. What is subadditive function? So a function f on some certain domain is called subadditive if f of x plus y is less or equal to fx plus f of y. So here we have to show that we have to show visually that sine of a plus b is less or equal to sine a plus sine b, provided a plus b is less or equal to pi. We have to show it by visually. Okay. Sorry. Just. So, what is subadditive function? Just a minute. Function is called subadditive if f of x plus y is less or equal to fx plus f of y. So here we establish that sine function is subadditive if that's a plus b is less or equal to pi, and that proof is totally visual. Okay. So for that we need one well-known result, that if it is A and this is B and the angle is C, then what is the area of this triangle? Area actually half AB sin C. We use this result to visualize this picture. Okay. So you see that we take x1, x2, xn such that sum of them x1 plus x2 plus xn is less or equal to pi. Okay. So just we take this angle. This is x1 angle x1. This is actually x2, and then this is x3, and onwards lastly this is xn. Okay. Now now we see that, and this is the total angle x1 plus x2 plus xn. Okay. Now we consider a circle of radius 1. This is the circle of radius 1. So this is the radius, and the radius is actually 1. Okay. Now you look this triangle. Here you have one triangle, right? You have one triangle. This is a triangle. Okay. So what is the area of this triangle? The area is half, side is 1 and 1 multiplied by 1, and sine of angle between that sides. This is actually x1 plus x2 plus xn. Okay. And now you consider this triangle. This is a smaller triangle. What is the area of this triangle? This triangle, area of this triangle is half 1 into sine of x1. Now what is the area of this triangle? Area of this triangle, this is half multiplied by 1 into 1 sine of x2. And similarly, so what is the total sum of all those smaller triangles? So this is actually sum of half sine of xn, and okay, the sum. Okay. Now you look this figure. You see that this smaller triangle has the smaller area than all the triangles. So from figure it is clear that this sum is less or equal to this sum. So this figure tells us that sum of sine of xn is less or equal to sine of sum of xn. So this proof is totally visual. Okay. So sine function is subadditive if their angles, sum of their angles is strictly less than pi. Okay. Next we present another visualization that tan function is superadditive. I will give some reference after this lecture. Okay. Okay. So next we will show that the tangent is superadditive. Okay, we will present visually this thing. So we will present the tangent function is superadditive. So when a function is called superadditive, a function on a certain domain is called superadditive if f of x plus y is greater or equal to f of x plus f of y. Okay. Just here I mention one thing. You know the definition of additive function. A function f is called additive if f of x plus y equal to f of x plus f of y. then the function is called additive function. And you are familiar with this definition when you learn continuity or linear transformation. But here we are using superadditive function and subadditive function. Okay. Okay. So here, superadditive function is a function f on a certain domain if f of x plus y is greater or equal to fx plus fy. Okay. Here we have give some visualization that tangent function is superadditive when there's the sum of the angles is equal to pi by 2 under this restriction. So this is the actually proof. This is the actually proof. And when you see this proof in some textbook, in some books or reference book or some paper, they only did only this picture. No words are there. They just draw this picture, and this picture is sufficient for this proof. But here I explain it. Okay. So we are considering the angle x. So this is the angle x1. Then this is the angle x2. And x3, lastly x, this is the angle xn. Okay, and now we are considering a right angle triangle. We are considering a right angle triangle where the length of the base is 1. Okay, and this angle is x1. This angle is x1 and the base is 1. If base is 1, so what is the length of the height? What is the height? The length of the height is obviously 10x1. Okay. And similarly, if this is actually x2, then just we considering this rectangle, this right angle triangle. So then this height actually 10x2. Okay, and similarly, if it is this angle is xk, so this length is 10 of xk because this is a right angle triangle. Okay, now you look at the bigger right angle triangle. This is a bigger right angle triangle. Okay, so and sum of those angles is actually sum over xk. Okay, runs from 1 to n. Okay, and this length is actually 1. So what is the length of height? So height is actually 10 of x1, x2, xn. Okay, so this height is actually tan of sum over xn. Okay, and here this length is tan x1, this length is tan x2, this length is tan xk, and lastly this length is tan xn. Okay, now we recall one result. If we draw a straight line and one point outside of the straight line, so what is the minimum distance? Minimum distance is the perpendicular distance, and this is a very easy result. So this is the minimum. Okay. So here you look, this distance is less than this distance. Okay. Similarly, this distance is less than this distance. This distance is less than this distance. And lastly, this distance is less than this distance, and this distance is same. So here you see that some of these distances are strictly less than length of this straight line. Okay. So tan x1 plus tan x2 plus tan xn, this summation is strictly less than tan of x1, x2, xn. Okay. So this figures tells us that tan function is superadditive, and you see that sum of these angles is strictly less than pi by 2. The sum is strictly less than pi by 2. Okay. So tangent function is superadditive. Okay, and this proof is given by Rob Pratt. Okay. Next we present another thing. Okay, that is, E and pi are transcendental number. If I ask you to give examples of transcendental number, then the very common examples are E and pi. Okay, so E and pi are two transcendental numbers. Here we compare two real numbers, pi to the power e and e to the power pi. Which one is bigger? In this figure actually tells us that pi to the power e is strictly less than e to the power pi. Okay, we explain this figure. Okay, we are going to explain this figure. Okay. Here, we consider a curve y, the function y equal to 1 by x. Okay, so we are considering one curve function a from the domain of the function is open interval 0, infinity to r. Okay, so this function, you know, this function is the convex function. Okay, this is actually convex function. This is actually convex function, and actually we are using this property. So, and also you know that the E is strictly less than pi. Okay, E is strictly less than pi. Okay, so just we draw the graph of the function. This is a graph of the function. Okay, and we take 2 points, x equal to E and x equal to pi on x-axis. Okay, now we consider a rectangle. We consider this rectangle. Okay, this rectangle. So this is the rectangle we are considering. Okay. Now, what is the area of this rectangle? Area of the rectangle. Rectangle area. What is the area of the rectangle? So actually, length is actually pi minus e. Okay, and the height of the rectangle is actually this is actually point E. So this height is actually 1 by e, because we are considering the graph of the function 1 by x. Okay, so this area is actually pi by e minus 1. Okay, now we are considering the area of this curve, this shaded region. Okay, so this is the actually we are considering the area between this region. Okay, we are considering this area. Okay, this area. So you see that this curve is continuous on this domain. Okay, continuous. So obviously this is a Riemann integral. So this thing actually exists, and you know the geometric meaning of Riemann integral is nothing but the area. So we are using that concept. So that area is this. Okay, and so this is nothing but the integration is log pi minus log e, that is actually 1. Okay, and you see that from this figure tells us that that area, okay, is strictly less than the area covered by the rectangle. Okay, the rectangular area is bigger area. Okay, just now you just simplify. So this is actually nothing but log pi is strictly less than pi by e, and this is nothing but, so pi to the power e is strictly less than to the power pi. Okay, so this is the proof. Okay, but if you look at the paper, that figure is sufficient, that the pi to the power is strictly less than e to the power pi. Okay, and again this is my another paper. Okay, that paper is published in Mathematical Intelligencer. Okay, this visualization is again a paper. Okay, of mine. Okay, next we demonstrate another way to visualize pi to the power e is strictly less than e to the power pi. Okay, this is another way. Actually, I want to focus that any kind of result, any kind of ideas can be visualized in different ways. Okay, so this is another way to visualize that pi to the power e is strictly less than e to the power pi. Okay, so we explain this one. Okay, just a minute. Okay, so look at this picture, picture. So here we consider the function y equal to log x. Okay, y equal to log x. Okay, and at the point x equal to 1, we consider the tangent to the curve. Okay, so the equation of the tangent line is y equal to x minus 1. Okay, so you have a curve y equal to log x, and at the point x equal to 1, you consider the tangent y equal to x minus 1. Okay, just a minute. Just so you consider what you consider consider the curve y equal to log x, okay, and at that point at x, just a minute, you consider the this is a tangent line, this is a tangent line, and the equation is y equal to x minus 1, okay, y equal to x minus 1, okay. Now look, e is strictly less than pi, right? So pi by e is strictly greater than 1. So you consider the tangent at the point x equal to 1. So obviously pi by e lies just right side of x equal to 1. Okay. Now you consider a line. Sorry, just you consider the line at the point x equal to 1, x equal to pi by e. Okay. Just you consider this. So okay. So you consider the line segment at the point x equal to pi by e. Okay. So you see this length QR, this length is actually log of pi by e. Okay. So you see that the length QR is actually log of pi by e. Okay. And the length PR is actually pi by e minus 1. So you see that PR is actually pi by e minus 1. Okay. And from figure you see that the length PR is bigger than the length QR. Okay. So the length PR is bigger than the length QR. So obviously pi by e minus 1 is bigger than log of pi by e. That is actually log pi minus 1. Just then simple calculation you can derive the inequality pi to the power e is strictly less than e to the power pi. Okay. So here we are considering that y equal to x minus 1 is tangent at the point x equal to 1 to the curve y equal to log x. Okay. And this proof is actually given by my UG student Anando. Okay. When he was at a first semester student, okay, just after taking admission in our college, one day he came to me and show, sir, we can visualize this, okay, and later it published in a journal, Mathematical Intelligence, sir. Okay, so this paper, this visualization was given by Anando, my student. Okay. 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 Next, we are going to visualize a more general inequality that a to the power b is bigger than b to the power a when a and b are two real numbers, both are bigger than e and b is bigger than a. Okay. So we are going to demonstrate this and this is the general settings, general visualization, because if you take a equal to e and b equal to pi, then you get the result e to the power pi, the comparison between e to the power pi and pi to the power e. Okay. Okay, so we are going to explain this figure. Okay. This is a more general result. Okay, so here we consider the curve y equal to log x. Again we consider the curve y equal to log x. Okay, so we consider the curve y equal to log x. Fine. Now this point is actually 1 and you are considering two real numbers a and b such that a is strictly less than b and a is greater or equal to e. Okay, this is figure. Okay, now you just consider, just join this point. This is a line segment at the point x equal to a. This is the line segment at the point x equal to b. This is the line segment at the point x equal to e. Okay, Now you join this point. Sorry, just a minute. This point and this point. Just look at this figure. You just join this point and this point by a line segment. I mean this point, and this point by a line segment. Okay. Actually, my drawing is not proper. That's why. Okay. Just for that, just look this figure. Okay. And again, join this point and this point, this point and this point by another line segment. Okay. If you have 2 points in plane, you must join by a line. Okay. So this is Euclid axiom. Okay. So yes, we can join this. Okay. So you join origin and that 2 points. Okay. So you see that these are the lines. These are the lines passing through origin. Okay. So the equation of those lines looks like y equal to mx type. Okay. So we consider this equation as y equal to max and this equation as y equal to mbx. Okay. Now look, this angle and this angle and this angle. Okay. So you see that this angle is bigger than this angle. Okay. So obviously tan of this angle is bigger than tan of this angle, right? So obviously MA is bigger than MB, right? Okay, MA is bigger than MB. So what is MA? MA means this is actually log A. This is actually log A by A. Tangent means perpendicular this by base. Okay, perpendicular by base. So log A by A is bigger than log B by B, and then you just simplify it. Okay, so you have the desired inequality. Okay. And this inequality, this result, this visualization was given by Galland, Charles Galland. Okay. So this is a visualization to the famous inequality a to the power b is bigger than b to the power a, where a and b are 2 real numbers with that property. Okay. Okay. Next, we are going to visualize another famous inequality. You know E. If I ask you, give me some example of transcendental number. So the first, maybe the first example is E, and you know that E lies between 2 real numbers 2 and 3. Here we give a visualization that E lies between 2 and 3. Okay. 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 So if I ask you what is the definition of E, we can define E in 2 ways. Okay. So one is by using series, or another one is using calculus. Okay, so first we define the log function. The definition of log function is in this way: log of x equal to dx dt by t. Log of x equal to integration 1 to x dt by t. So this is the definition of log function. And what is the definition of E? E is defined as that E is a number for that integral value. That integral value is 1. So this is the definition of E. Another one definition of E, that E is a real number such that integral value 1 to E is 1. Then that real number is called E. So this is the definition of E. There is another definition using series. Okay, there is a sequence. You know that xn equal to, if you consider the sequence xn equal to 1 plus 1 by factorial 1 plus 1 by factorial 2 plus up to 1 by factorial n, then you can show that this series is bounded above and amount on increasing. So this series is convergent. So that converging point is called E. This is another definition of E. So here we define E in this way. Okay, and both two definitions are equivalent. Okay. Now, actually, we are going to show that 2 less than E less than 3. So this statement is equivalent to show that L2 is strictly less than 1, strictly less than L3. Okay. So actually we have to show that L2 is strictly less than 1 and 1 is strictly less than L3. We have to show this. Okay. Now, what is L2? What is L2? L2 is this area. So L2 is actually integration 1 to 2 dt by t, this area, the L2, and you just look at this square. Look at this square. Okay. This square. Okay. So what is the area of this square? Area of that square is, the length is actually, this length is actually 2 minus 1, okay, and that height is actually 1, so that area is actually 1, okay. And from this figure you can visualize that the area of this rectangle is bigger than L2, okay. So obviously L2 is strictly less than 1. That means 2 is strictly less than E. So one part is done. So this part, this figure, this portion actually implies that E is a number which is bigger than 2. Now we are going to explain that L3 is bigger than 1, that is E is strictly less than 3. So we are going to explain that one. Okay. Okay. Now think what is L3? Now we are considering L3. What is L3? L3 is the area integration 1 to 3 dt by t. Okay. So L3 is this area. L3 is just look this area. Okay. L3 is this area. Okay. L3 is this area. Okay. So we can think L3 is this area. Now we break this area into 3 parts. Okay. So for that we draw a line parallel to this line through this point. Okay, just to join this. Okay, at the point x equal to 2, at the point x equal, if this is a point x equal to 2, so obviously this point is actually the coordinate is 2 comma half. Okay, because this is the graph of y equal to 1 by x. So at this point we draw a parallel line and parallel to this line. Okay, this is a line. Okay. So look, what is the L3? So L3 can be think as area of this portion plus area of this portion, and then area of this portion, just this portion, okay, this portion, okay. So this is actually L3, okay, this is actually L3. Now we consider the area of this rectangle, okay, this bigger rectangle. So this is actually L3 part. Now we consider the area of this bigger rectangle, this rectangle, okay, just consider this rectangle. So what is the area of this rectangle? See, the length is actually, this is 1, this is 2, this is 3, so length is actually 3 minus 1, okay, and the height is actually half. Height is actually half. So this is area is actually 1. Okay. Now this area can be think as a sum of 3 portions. This portion, okay, plus this portion, and this portion can be written as, just think on this portion, okay, plus this portion, okay. So we can think the bigger area of the bigger rectangle is as sum of this 3 portion, and L3 as sum of this 3 portion. Okay. Now just we compare those areas. See, L3 and this rectangle has this area common. Okay. And now just a minute. Okay. And L3 has another portion, this portion. L3 has another portion, this portion. This is this portion, okay. And that area has again that portion. Okay. So these two area has 2 common portion. This one is same as this one is same as this one. So in L3 this one is left, and in the area of a rectangle this one is left. Okay. Now what we did here, we rotate this portion by 180 degree, by 180 degree angles. Okay, just we take the reflection. We take the reflection about this line. Okay, that is actually we give a rotation this lines this curve by 180 degree. Okay, so you get this line. Okay, now look, this area is same as this area. Okay, so this area is same as this area. So naturally you see that this area is strictly less than this area. You can visualize it if you give a rotation this portion by 180 degree. Okay. So here you see that this area is bigger than, this is bigger than this portion. Okay. So L3 has three portion, 1, 2, 3, and that area has three portion, and among them these two portions are same, only these two areas are left, and if you compare by giving a rotation, you see that this area is bigger than this area. Okay, so obviously from this explanation you can say that L3 is bigger than area of this rectangle. Okay, and area of this rectangle is actually 1, so L3 is bigger than 1. That means 3 is bigger than E. So E must be, so E is strictly less than 3. So that is the inequality 2 less than E less than 3. Okay, and this is a nice and beautiful visualization that E lies between 2 and 3. Okay, and this visualization is given by Nick Lord. Okay. Okay. Now we will present some elegant visual demonstration of some result related to limits. Okay, we learn some limit results in our 12th standard class or in UG class. Here we give two visual proof of known results, two known results. Okay, first we establish that the harmonic series is divergent. Okay, so this figure, actually this figure demonstrates that the harmonic series is divergent, and we will explain it. Okay. Okay. So for that, again we consider the graph of the function y equal to 1 by x. We consider the function, this function where f of x is given by 1 by x. Okay. And this function is convex function. Okay, and we know that harmonic series is actually, what is harmonic series? What is harmonic series? This is sum of this actually. Okay, 1 plus half plus 1/3 plus 1/4 plus onwards. So this sum actually plus infinity. That means this does not converge. That means that sum is bigger than any given real numbers. Okay, we have established by this figure. Okay, for that we consider the points on x-axis. This is a point x equal to 1. Then we consider the point x equal to 2, x equal to 3, x equal to 4, and lastly x equal to n, and then n plus 1. And this is a curve, a graph of the function y equal to 1 by x. Okay, now we consider this rectangle. Actually this figure is very much similar to Riemann sum. If you think Riemann sum, then this is actually similar to that. Okay, so then we consider a line segment at the point x equal to 1, then x equal to 2, x equal to 3, x equal to 4, lastly x equal to n, then x equal to n plus 1. Okay, and we draw rectangles in this way, right? Okay. Okay. So now what is the area of this rectangle? The area of this rectangle is, the length is actually 1. Okay. And the base is actually 2 minus 1, that is 1. Okay. Then what is the area of this rectangle? The height is actually half. And the base is actually 3 minus 2, that is 1. That is 1. That is 1. Okay. And similarly area of this thing is actually 1/3. Okay. And area of this thing is actually 1 by n. Okay. So area of all those rectangle is this sum. So this is actually 1 plus half plus 1/3 plus 1 by n. So this is actually area of all those rectangles. Okay. Now we consider the area bounded by the curve y equal to 1 by x, we consider this area. Okay, area bounded by the curve y equal to 1 by x, x axis, and x equal to 1, x equal to n plus 1. Okay, so we are considering the area, this area. So this area is actually this thing. Okay, and what is this area? This is actually log of n plus 1 minus log 1, that is 0. Okay, this area. Now from this figure you see that the area of those rectangles is bigger than the area bounded by the curve y equal to 1 by x, x axis, and x equal to 1 and x equal to n plus 1. Okay, so this figure tells us that this sum is bigger than log of n plus 1. Okay, and you know that log x is strictly increasing function. Okay, so this quantity goes to infinity as n goes to infinity. So obviously this quantity can't converge. Okay, so obviously the sum of these numbers is plus infinity. Okay, so harmonics diverges, and this figure tells us that result. Okay, and this is very familiar result. If you Google it, you can find this picture. Okay, this is very famous. Okay, thing. Okay. So next we establish another thing, that the limit of this function, limit of 1 plus 1 by n whole to the power n as n tends to infinity is e. Okay, and this is the last visualization. Already we have reached our time. So this one is the last one. Okay. Okay, so again here we actually the curve the function f from open interval 0 to infinity to r defined by fx equal to 1 by x. This curve is very beautiful curve. That curve has a one property, that is this is convex. Okay, using this property we can give lot of visualizations. There are lot of visualizations using this curve. Okay, and you see that today we explained many results using this curve. Okay, so this curve is very beautiful. Okay, so again we consider the graph of the function y equal to 1 by x. Okay, now we consider the point x equal to 1, and then we consider the point x equal to 1 plus 1 by n. Okay, now we consider a rectangle by this way. So what is the area of this rectangle? The area of this rectangle is, the length is, that length is 1. Okay, and the length of the base is actually 1 by n. You see it. Okay, now what is the area of this bounded region bounded by the curve y equal to 1 by x, x axis, and x equal to 1 and x equal to 1 plus 1 by n? What is the area? That area is actually integration 1 to 1 plus 1 by n dt by t. Okay, and you see from this figure that the area of the rectangle is bigger than the area covered by the curve y equal to 1 by x and x axis, and x equal to 1 and x equal to 1 plus 1 by n. Okay, now we join this point such that this line segment is parallel to this line segment. Okay, so now what is the area of this portion? Area of this portion, so the length of this portion is actually 1 by 1 plus 1 by n, and this length is actually 1 by n. And from this figure you see that this is actually strictly less than this integration. Okay, now you just simplify it. So if you simplify it, so you have just simplify it, n by n plus 1 multiplied by 1 by n, and strictly less than, this is actually log of 1 plus 1 by n, and this is strictly less than 1 by n. So that is actually n by n plus 1 is strictly less than log of 1 plus 1 by n whole to the power n strictly less than 1. Now you just take the limit or apply sandwich theorem. So limit of log of 1 plus 1 by n whole to the power n equal to 1 as n tends to infinity, and that means since log is continuous function, you know, and exponential function is continuous functions, so obviously this goes to e. Okay, so this is our visualization that limit of function is z. Okay, and I stop here. Actually visual proofs, we say this is a visual proof, but many times it needs some words to explain. Okay, so all times it is not actually proof without words. Many times it needs words. Okay, so if undergraduate students can, if they want, they can do this kind of mathematics when they have recess time. Okay. And this is the references. There are some papers of mine. This is my papers, and this is the papers of other writers. And this is a book written by Roger B. Nelson, Proof Without Words. Okay, this book is published by Mathematical Association of America. So this in that book you have lots of visual proofs. Okay, and the same author has another book. That's part 2 of that book. That is published in 2000. That is again Proof Without Words, part 2. And in 2015, he wrote a third part of that book. This is again Proof Without Words. So those are the good books if someone wants to see visual proofs or proof without words. Okay, thank you. Yes, sir. Actually, we are the arguments we used here. That is actually length of straight line or area of a bounded region. Okay, so you know that area can be negative in usual sense. Okay, so that's why we can't take negative numbers. Okay. Okay, just a minute. Okay, let me explain. Let us take two real numbers. One is A and another is B. Okay. So your question is, what about the negative area? Okay, first of all, I already said that we are considering the idea that area of a unit square is 1. Okay, and I already said that this is an axiom. You can't prove this. This is an axiom. If you go through the definition of area, there are several axioms. So this one is one of them. The area is positive, and using this, if A is positive, and if A is positive and B is positive, using this idea, you can prove that the area of a rectangle is AB. Okay, you can prove it. Okay. So here in our discussion, we always take A is positive and B is positive. Now your question is, what about this area? Is that area, what about that area? Okay. So if we take any two real numbers A and B, you know there is another axiom. If you start to learn real number system, so first we state what is order axiom. Okay. So there is a starting point of real analysis is order. First is then order axiom. So in order axiom there is law of trichotomy. So if you have two real number A and B, then you can always there is axiom. By that axiom you can say that either A is bigger than B, or A is equal to B, or B is bigger than A. Okay. So since A and B are arbitrary real numbers, so this case is same as this case. Okay. Because if B is bigger than A, then we consider B first, then A. So we don't consider this one. Okay. So since A and B are two positive real numbers, so there are two possibilities. Either A is bigger than B, or A equal to B, and this follows from law of trichotomy. Okay. So if A is bigger than B, then this figure is fine. Okay. And you see, so there is a positive area. Okay. And what happens if A equal to B? Just to draw the picture, if A equal to B, so this is actually nothing but maybe this kind of separation. So there is no area. So that area is actually zero area. So that's why that equality came. AM get out equal to GM. That why this kind of equality came. You know, if you go through the usual proof, weighted AM get out equal to weighted GM, and that kind of things, then that kind of equality occurs if that vector is linearly dependent like that. Okay. So this kind of ordered pair is some lambda times of that kind. So that means here A is 1 times of B. That's why equality comes actually. And in that case, that area is actually 0. And if B is greater than A, then you just take this is A and this is B. Okay, actually this is actually commutative like that. Okay.
Yes, sir. Yes, sir. Infinity. Yes, sir. Yes, sir. Yes, sir.
Okay.
Okay, sir.
Now we came to the end of this today's seminar. It is a vote of thanks, is a part of this seminar. Now, Honorable Principal of Garbeta College, Dr. Hari Prasad Sarkar, Professor Madhumangal Pal, Professor Sujit Kumar Sardar, Professor Saurabh Das, Professor Vikas Chakraborty, the participants of the webinar coming from various colleges, faculty members of our department, students, ladies and gentlemen. It is my privilege to propose the vote of thanks in this webinar. In the enrichment program for students and teachers, this is first phase on linear algebra, analysis and differential equations. I take this opportunity to express our profuse gratitude and sincere thanks to the principal of Garbeta College for his esteemed presence among us and presiding over the function. The valuable thoughts he has expressed on this occasion will no doubt serve our college in footsteps to proceed further in the direction of development in teaching and research. Thank you, sir, for your encouragement and sagacious advice and guidance. We promise never to forget the keynote speech of Professor Madhumangal Pal, professor in mathematics, Vidyasagar University. I also feel proud to have him as a keynote speaker in this webinar. His benchmark lecture inspires us to put our thought in the series of resourceful and illuminating discourses under the webinar. In addition, I will also entrust our students to research in algebra and analysis. I pay my heartiest thanks to Professor Pal for his innovative lecture. Thank you, Professor Pal. Lecture presented by Professor Sujit Kumar Sardar, Professor in Mathematics, Jadavpur University, has really touched the heights and fulfilled the aim we envisaged. On behalf of the department, I convey my gratitude and heartfelt thanks to Professor Sardar for accepting our invitation and consenting to deliver webinar talk. His erudite talk on the topic illuminates various directions of the subject. Thank you, sir, for your gracious presence and wonderful delivery of speech in this webinar. I deeply indebted to Dr. Saurabh Das, Assistant Professor in Mathematics, NIT Jamshedpur, for his kind spare of time for Garbeta College webinar. His painstaking exposition and annotation reroute the subject topic on orthogonal polynomial to a comprehensive position. Many thanks to Dr. Das for his enlightening presentation that makes the subject matter easily grasped. We are happy to mention our obligation to Dr. Vikas Chakraborty, Assistant Professor in Mathematics, Rohada Ramakrishna Mission Centenary College, Rohada, for accepting our invitation and delivering his lecture today. His attractive deliberation deserves appreciation of excellence in teaching and research in the context of subject mathematics for visualization of mathematics in geometry and visualization processes. Let me express my gratitude and thanks to Dr. Chakraborty for his lecture. I put forward my special thanks to all the distinguished dignitaries in the audience who spare their valuable time and be with us in the 2-day seminar. I would also thanks to President GB of the college and its members, coordinator of IQAC, various college committee conveners and its members who are directly or indirectly extended their support and inspiration to organize the webinar. I take the opportunity to thanks to participants, professors, esteemed dignitaries and students for their presence and participation in the interactive session. Our kind of words and appreciation also go to my colleagues Dr. Abhijit Banerjee and Dr. Rajlakshmi Mukherjee for their tireless effort to organize this webinar. I offer my sincere gratitude and thanks to all the departmental teachers of mathematics departments and staff, also to the faculty of Garbeta College and staff. Finally, I solicit your continued support and encouragement to march forward in our quest for knowledge. Thank you, sir. Thank you. Thanks all of you once again. Thanks. I would like to request Dr. Rajlakshmi Mukherjee to end this, declare the end of this session. Rajlakshmi, hello. So if he is not there, I would like to request Dr. Banerjee to declare the end of this session.